For those of us that were not in AP chemistry, or for chemistry was like ages ago and we don't really remember this stuff, it's okay. We're going to do a little gas laws review. So if you pretty much get this, you can kind of skip this part. We're going to base our discussion basically on the ideal gas law, PV equals nRT. We need to know in physics what pressure is. And pressure is our force divided by our area, so its units would be newtons per square meter. Now, most of the time we don't use that as our unit. We rename that a Pascal, and its abbreviation is PA. So, atmospheric-wise, if we were going to look at some ways to convert, the SI unit for pressure is this 101,325 pascals. Now, sometimes you can use atmospheres, but most of the time we're going to be using pascals. But if you're not using the gas constant R in your equation, you can pretty much use any of the 4 units for your pressure calculations. 1 atmosphere is the same thing as 760 millimeters of mercury, same thing as 101,325 pascals, or 101.3 kilopascals. And if we needed to convert any of these units, we can just use the T-bar. So if we had ATMs here, we could switch between ATMs and pascals, or we could switch and we had, let's say, millimeters of mercury here. We were trying to convert it to pascals. We'd use millimeters of mercury down here. And 760 millimeters of mercury is 101,325 pascals. So whatever conversion we need to do is just a T-bar. So that's nothing weird or anything. So most of our gas laws can be derived from this ideal gas law equation. And in PV equals nRT, let's say we had constant temperature and constant moles. Okay, so this whole side is a constant. So as the pressure increases, in order to keep this side here the same number, the volume is going to decrease. And you kind of have an idea of that. If you take a gas and you apply more pressure to it, it's going to get smaller. So your gas is going to get smaller. So as you squish a gas, it's going to get smaller. It's kind of like duh. So as you get more pressure, your volume is going to get smaller. So that's an inverse relationship. And if we were going to see it on a pressure volume graph, an inverse relationship looks like that. And this is one of the pretest questions in the beginning. So if we were going to make this into a proportional relationship, they'd be inversely proportional, and we would just say that P1 V1 is equal to P2 V2. And that would be the equation we would use if we had the same number of moles of gas and the same temperature. So the only thing that's changing is the pressure and the volume. Taking our same PV equals nRT equation, if the volume was constant, so sometimes we talk about a constant volume thermometer, and it's a thermometer that uses the change in pressure of the gas to measure the temperature. So our volume is going to be constant, our number of moles is going to be constant, and our temperature is going to be constant. So we're going to move everything that's going to change on one side and everything that's going to stay the same onto the other. So this is going to be P over T is equal to nRV. And this whole part over here is constant. So our equation will become P1 T1 equals P2 T2. And that's a directly proportional relationship. That's a proportion. That's what a direct proportion relationship would look like. So what if the pressure was going to remain constant? What would happen? Well, the pressure is going to be constant, N and R are going to be constant. So again, we're going to move all of our constants to one side, and our moving things or changing things over the other side. Oops, this is a P. And this is our constant. And so this becomes Charles' law, V1 over T1 equals V2 over T2, which tells us that the volume and temperature are directly proportional. And here's a little, pay attention. This temperature has to be in kelvins. Whenever we're working with a gas, whenever you are working with a gas, this temperature always has to be in kelvins. So you're going to take your kelvins is going to equal your degrees Celsius plus 273. So you always need to add that 273 to your degrees Celsius. Well, what do we do if everything's changing except maybe the number of moles, the amount of gas? We have it in a fixed container. Well, again, we're going to move everything that changes to one side. So PV over T is going to equal NR, and this is our constant. So this becomes our combined gas law, P2V2 over T2. But do you see how all of the equations are derived from PV equals nRT? And since we've kind of taken this factor out, your pressures just need to be in the same unit, your volumes just need to be in the same unit, but your temperatures have to be in kelvins. That's the only thing that has to be in the same unit. Now, if you always wanted to make sure you did it right, you would always change your pressures to pascals. Your volumes, we're in physics now, are going to be in cubic meters, okay? And your temperatures would be in kelvins. So what would you do if you had to use PV equals nRT? Okay, you're going to use this pretty much when they give you the number of moles. Now on the pretest, it gives you grams and you have to convert your grams to moles. I'm going to give you the number of moles. So I'll just go ahead and give you the number of moles of gas. But your pressure needs to be in pascals, your volume in cubic meters, and when you do that, your value for R is going to be 8.314. And it actually has units of joules per mole Kelvin. Okay? Because remember, pascals are newtons per square meter. And then you're going to multiply that by cubic meters, and you're going to be left with a Newton meter. Well, a Newton meter is a joule. How about that? So the SI units still work out. If you're going to use atmospheres, the value for R is 0.0821 atmospheres liters over moles kelvins. And you'll see sometimes on the pretest I did do that just because I was too lazy to do all my conversions. So that's a little gas law review for you, and if you have any questions, make sure you please ask them during class.